Welcome to a deep dive into the future of flavor. Today, we're exploring technology infusion spirals, the precision-engineered tool redefining how we age the world's finest beverages. To truly understand this technology, we have to look at the legal and engineering blueprint. Let's dive into the core patent that changed the maturation game forever.
This document is the smoking gun of precision aging. It details the exact geometry required to maximize wood contact and bypass the limitations of the traditional barrel. To really grasp the mechanics involved, I highly recommend watching this technical overview. It breaks down the patented design that makes this rapid extraction possible. Let's watch.
This precisely machined, deeply toasted wooden cylinder is a highly specialized industrial apparatus. It was engineered to overcome the specific chemical bottlenecks inherent in large-scale liquid aging. For centuries, the process of oak aging has suffered from severe mechanical limitations. The traditional process is exceptionally slow, the chemical extraction is highly unpredictable, and the physical storage footprint is massively space inefficient. The root of this systemic inefficiency lies in the traditional oak barrel itself. The physical requirements to build a watertight wooden structure actively fight against the chemical requirements needed to efficiently age the liquid inside. When a highly reactive liquid remains in a wooden vessel for years, the volatile compounds slowly break down the barrel walls. This degrades the wood's structural integrity, inevitably creating microleaks that ruin valuable batches. This is U.S. Patent 7357069B1. It documents a precise engineering solution to the barrel problem, the beverage infusion spiral. The core mechanism relies on grain manipulation. By mechanically orienting the longitudinal wood fibers, the apparatus directly forces liquids out of a state of slow passive diffusion and immediately triggers rapid, predictable capillary infusion. By isolating the specific fluid mechanic, the invention decouples a liquid's chemical aging process from the physical limitations of its holding vessel. To understand why the spiral works, look at how traditional oak staves fail. Notice the parallel grain running along these disassembled, charred segments. To prevent a barrel from leaking its contents onto the floor, coopers would cut the staves to expose what is called the face grain. By definition, face grain is naturally resistant to liquid penetration. Because the liquid cannot easily penetrate the face grain, chemical extraction is strictly gridded to the shallowest layers of the wood. The liquid must rely entirely on passive surface diffusion, a process measured in years. Historically, producers tried to bypass the barrel entirely by dropping modular inserts directly into a tank. The primary goal of these loose chips and cubes was simply to increase total surface area. But loose chips fail a basic test of fluid mechanics. When dumped into a vessel, they stack unpredictably. This dense packing creates chaotic fluid channels and massive dead zones where no liquid actually circulates, halting the chemical exchange. Furthermore, chopping wood into tiny, randomized pieces obscures the raw material's origin. It becomes impossible to spot defects, allowing knotty core wood to leach harsh compounds into the batch. Simply maximizing surface area is an inadequate engineering solution. To achieve rapid aging, the geometry of the wood must guarantee uniform fluid exposure while maintaining a size that allows for rigorous quality control of the base material. This cross-section from Figure 3 of the patent details the specific internal geometry required to solve both of these fluid dynamic problems. At the core of the apparatus is a continuous, unbroken structural spine running exactly down its center. The critical engineering requirement dictates how raw lumber is selected. Natural wood fibers must run exactly parallel to this central axis. From this aligned core, the machine mills a continuous spiral groove, creating a series of deep, opposing ledges across the cylinder. Because fibers are strictly parallel to the axis, slicing these planes cuts straight across the grain. Instead of the closed face grain of a stave, this geometry exposes massive amounts of open end grain. Oak end grain acts like a dense bundle of microscopic drinking straws. When liquid hits these severed vessels, it doesn't just sit on the surface. The fluid dynamics immediately shift. The liquid abandons passive diffusion and is actively wicked deep into the wood's internal vascular structure through capillary action. This rapid internal transport system forces the liquid through the wood matrix at a highly accelerated rate, speeding up the extraction of complex esters and the binding of harsh aldehydes. This spiral geometry aligns external fluid pathways with the wood's internal capillary network, maximizing reactive efficiency. Translating this fluid dynamic theory into industrial reality requires precision. Producers must mill thousands of these uniform spirals without snapping the parallel grain structure. Figure 5 outlines the patent's fabrication schematic. Raw wooden rods load into a receiver funnel for controlled single-file intake. As the rod descends, guide rollers grip the wood, locking in strict longitudinal alignment while dictating the precise rotational speed. Figure 6 documents an alternative feeding mechanism. These large, spirally fluted elastomeric rollers provide an aggressive grip and consistent rotation without denting or damaging the wood's exterior. As the rod is fed downward, it meets the primary cutting mechanism. The blade is precisely calibrated with a built-in structural safeguard. It is programmed to stop just short of the central axis, leaving a continuous, solid spine completely intact. Leaving this core intact guarantees exact, uniform spacing between every spiral plane. It prevents the wood from compressing, eliminating the fluid choke points that plagued the loose chip method. Once the machining is complete, the entire spiral undergoes a highly controlled thermal toasting process to activate its specific chemical and organoleptic properties. This assembly line successfully automates the massive generation of open-end grain surface area while completely preserving the physical structural integrity required for industrial deployment. Figure 4 outlines the deployment of the finished apparatus within a commercial liquid container. Instead of floating freely, a terminal fastener securely anchors the spiral directly to a standard barrel bung or tank lid. This design inherently features modular scalability. Facility operators can link multiple spirals serially, hanging them end-to-end to precisely calibrate the total extraction rate for massive industrial vessels. This top-mounted suspension permanently solves the logistical nightmare of fishing loose wood out of hundreds of gallons of liquid. The exact moment the target flavor profile is achieved, the wood is immediately extracted. Because this technology works in any vessel, producers can eliminate the need for vast warehouses dedicated to fragile wooden barrels, using inert storage instead. By deploying these engineered inserts, producers can utilize large, easily sanitized, and totally inert stainless steel tanks, while actively replicating the exact organoleptic chemistry of small-batch oak aging. These precise geometric cuts function as an integrated fluid transport mechanism. U.S. Patent 7357069.
It is fascinating to see how the patent specifically indicates that transverse grain exposure. It essentially turns a piece of wood into a highly efficient chemical extraction engine. The schematics proves this isn't just a trend, it's a patented shift in extraction dynamics, providing the control every modern producer has been dreaming of.
Yes, a game changer. Thank you for joining our deep dive into the science of wood. We hope this look at the blueprint helps you engineer your own perfect pour. Until next time, cheers!